So hello and welcome to a new year for those of you who care. Us Jews and stuff. Did anyone have any questions on any of the math that we've done so far? We've had a full week of math classes. That's one full chapter, and I believe we started the second chapter, right? So are there any questions on any of it? Now's the time.
I have a question.
Yes.
I finished the homework one, but I don't know how to submit it on the Canvas.
Nothing to submit. I don't accept, there's nothing to submit. The homeworks are done for your own personal benefit and understanding. And when it
So
comes
it's
to
our own practice for the homework one?
Yes, the quizzes and tests I base off of the homeworks. So if you do the homeworks, then you're in a prime position to do well on quizzes and or exams. And if you don't do the homeworks, you might have a little trouble.
Okay,
So the
got it.
homeworks are for your benefits and your benefit alone. Sound good?
Yeah.
I
Thank you.
actually had a question. Sorry.
Yes, I am completely
Actually had a
lost with chapter 2 so far. Well, one second, before you ask the question.
Okay. No worries.
Chapter 2, we just started, we did a little bit, we'll do more today. So hopefully, as we go through it, it'll make more sense. We didn't spend a lot of time on it. But let's hold off on whether or not you want to reassess your understanding level till later with the chapter. Is that okay? Because we'll be doing more situations that are more of the same. Okay, now what was your question?
Yeah, so I just want to make sure that I did it correctly. For chapter 1, number 7, regarding the tetrahedral dice, when it says construct a sample space for the equally likely outcomes for the two numbers on the bottom of the dice, I didn't really understand what that meant, but I wrote out every possible pair that you can get when rolling it, and I had 16.
Okay, and are those 16 all equally likely?
Yes.
Then that is a sample space of equally likely outcomes.
Okay, so I just wanted to make sure I did it correctly, that you get 16 outcomes. And for example, like for B, what is the probability that you roll doubles? You get 4 out of 16, which is 25%.
That's
okay,
correct.
Perfect. I just didn't understand what it meant by outcomes for the two numbers on the bottom. I thought they were just like looking for the outcomes at the bottom, but no. Okay, yeah, I just wanted to.
Yeah, that's just their terminology for the same thing. Like if you roll 2 regular sided dice, we care about the number that's on top, correct?
Right.
But with a tetrahedral dice, it's a pyramid, so there is no number on top. There's only a unique number on the bottom. So in that case, we care about the number on the bottom, but it's the same idea. It's like what you're rolling.
Okay, perfect. And then, sorry, one more question.
No problem.
Number 9, when it says, describe the 2 different ways that you could use to help them decide whether their method is fair. For the empiric, I said that it is fair because you can either get heads, heads, tails, tails, heads, tails, or tails, heads, which gives you like a 50-50 chance. Therefore, it is fair, but would that be empirical or would that be theoretical?
That would be theoretical because you didn't actually do any, you didn't actually roll it all to arrive at your conclusion, correct?
Right.
So that's purely theoretical. Empirical would be, let me roll it 100 times and see if we get roughly 50-50.
Okay, so I did it the other way. I switched it and I said, yeah, okay, but I got it. Thank you so much.
You're welcome so little. Okay, any other questions? All right, well, in that case, someone remind me, someone asked about the answer key. I believe, was the homework due today or was it due on Thursday?
It was due Thursday.
You mean it's due in 2 more days from now, correct?
Yes.
Right. So I'm not going to put up the solutions until the homework is actually due, because I want people to have the opportunity to do it without the temptation of just looking at the answers. So Elizabeth, if you want to ask me again on Thursday, I will put it up during, when class starts. Just say, hey, can you put up the homework? And I'll be more than happy to. Is that okay? All right. Otherwise, let's go to chapter 2. Let's open up the PDF. And let me share my screen here. And okay, so let's quickly recap what we're doing in chapter 2, which is a slightly more complicated section than the first one. And before I do it, just curious, on my screen, of course, I see the simulation, but I also see 6 people on the right. Do you guys see the people as well, or do you just see the screen? I'm not sure what is being shared with all of you.
I can see both.
I
You
think
see both?
The
I see the
simulation and
people,
then
but
you.
I'm sorry, say that
Great.
again. Say that again, please.
So
we
we
see your
Sorry.
I see 4 people on the.
Okay,
on
so
the- Yeah, it's the same pretty much.
okay,
I
so
see
the,
the simulation and 4 people on the right.
okay, so I just want to know what you guys saw versus what I saw. Okay, all right. So simulation. So again, what is the purpose of the simulation? There are times that you wish to run an experiment, and it's either going to be too lengthy to run the actual experiment, too time consuming, too money intensive, to this, to that. Different scenarios for different situations, but the basic idea is I don't want to actually do the experiment. I want to do a easier experiment which can model the situation in exactly the same way. So what's an example? Suppose well, I mean, we have the examples, here in the book. So, suppose just to recap the cigarette smoking model that we did last time, it is known, it's a fact. Okay, it's a known fact that 1/3 of students in high school in the Los Angeles school district have smoked or tried smoking at least once. Known fact. And what I want to do is I want to pick 12 students at random and ask them, hey, have you smoked? Have you smoked? Have you smoked? Have you smoked? And go through the 12 and count how many of the 12 have actually smoked. How would I do that? Well, I would drive down to some random school, and I could pick 12 people from that school. But of course, if I did that, then I'm only really getting information about that one school, and I want information about the entire school district. So really a better way would be to pick 12 different schools and then go and drive to each of the 12 schools and pick a random student from each of the 12 schools. And that can literally take all day, if not longer, to do that. So how can I simulate the experiment in seconds? So because there's a 1 in 3 chance of picking someone who smoked, all I have to do is create a scenario that has a 1 in 3 chance of getting one outcome and a 2 in 3 chance of getting a second outcome. So in the example of the spinner here, what I can do is I could go ahead and create a section that is roughly 1/3 of the entire area versus the other section, which is 2/3 of the area. And then I can flick the spinner and the spinner will land somewhere. Let's see, it lands right here. So that means that the spinner lands in the non-smoking section. And the first student that I just asked happened to be a non-smoker. So rather than spending an hour and driving down to some school over there and asking some random students, I took a second to flick the spinner, and I see that the first student that I asked was a non-smoker. Flick it again, get some result. Flick it again, get some result. Do this 12 times. Count how many times I landed in the smoking area, and that is equivalent to asking 12 people, hey, have you smoked? Have you smoked? And so on. I have simulated the experiment by doing a much easier experiment. This is what simulation is all about. And the key to simulation is always to make sure that the probabilities of your simulation match the probabilities of the actual situation. So if I wanted to use cards to generate a 1 in 3 chance, there's many ways of doing it, but I think the easiest way would be just to pick 3 cards, let's say those 3 right here, and ignore all the rest. So the rest throw away or just don't use, and say, this is my smoker, this is my non-smoker, this is a non-smoker. and then shuffle, pick. I get one outcome. That's one student. Shuffle, pick, get one outcome. That's my second student. Shuffle, do it 12 times. Each time, reshuffle the 3 cards, pick one, reshuffle. So perhaps my outcomes were smoker, non-smoker, 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 smoker, non-smoker, and so on. And then I just count how many smokers I have. And that's how many students that I asked said they were smoker. Again, a lot quicker than actually spending all day asking people. If I use dice, I need to create a scenario where I have a 1 in 3 chance, 2 in 3 chance. How can I do that? Well, if there's 6 outcomes, assign 2 of them for smoking and 4 of them for non-smoking, and now I have a 1 in 3, 2 in 3 chance. So cards can be used, spinners can be used, dice can be used, right? There's many situations of creating a simulation rather than doing the actual experiments. Okay, so that's just a recap. I think we did this. We definitely did this. We definitely did this. We did all this.
We're on page 9, I believe.
We're on page 9. Okay. So each time you design and conduct a simulation, follow these 3 steps. First one is you have to model the actual situation with the simulation. In other words, you have to create a scenario where the probabilities match for each possible outcome. Smoker, non-smoker, 1 in 3, 2 in 3. You have to create a model and you want to describe how you're going to use the random device to conduct a run of the simulation, whether it's dice or cards or spinners or whatever the case may be. Then match. It says state which outcomes of the device correspond to which outcomes in the actual situation. Dice, 1 and 2, smoker. 3, 4, 5, and 6, non-smoker. Cards, ace, smoker. 2 and 3, non-smoker. Assign your outcomes of your simulation to match the actual outcomes. Repeat. Do it over and over again. In our case, we did it 12 times because we had 12 students that we were asking. In the case of the kindergarten boys and girls, we did it 15 times. And then, of course, explain what you're going to write down. You don't write down the actual physical outcomes. Oh, I got a 7. Well, not a 7. Oh, I got a 2. I got a 3. I got a 5. I got a 6. No, I got a smoker. I got a non-smoker, right? Your outcomes are not the physical outcomes of the simulation, but rather what they correspond to for the actual scenario. And then, of course, conduct all the runs that you're going to do. And you want to visualize it. So you make a table, you make a graph or something like that. And then finally, come to your conclusion. Okay, I asked 12 students if they smoked. 11 of them said that they did. Well, I was working under the assumption that 1 in 3 smoked, which means I should have gotten something around 4 smokers by asking 12 people. I got 11. Maybe my model is incorrect. Maybe something's incorrect. Maybe my spinner's broken. Or maybe the dice are loaded or something. But you want to make a conclusion based upon your simulation about the actual scenario. Does that make sense so far? In theory, at least? We'll do a couple more examples, hopefully, but hopefully in theory, this is making a little sense. So we're not actually going to do this class activity because we're not actually there, but we can at least talk about it and what we would do in this scenario. So 5 students, A, B, C, D, and E, their parents didn't like them, so they gave them really strange names, have identical iPhones. They toss their iPhones on a table, and later each one picks up an iPhone at random. And the question is, how many students will wind up with their own iPhone? Now, we can actually do this experiment by having everyone bring their iPhones, or 5 people bring their iPhones and throwing them on the table and then mixing them up and picking one at random, or we can simulate it. How are we going to simulate it here? So it says use 5 index cards to design and conduct a simulation to approximate a probability distribution table for this situation. So how exactly would I use index cards to conduct one run of this situation? What would I do? I see a chat here. It says, you could color one index card of the 5 students, then have students draw it. What do you mean one index card? Why am I only coloring one of them? What does the color indicate?
I thought you would have to do like a 1 in 5 chance, right?
Well, each person has an iPhone, correct?
But getting yours is only a 1 in 5 chance, right?
If you picked when all 5 were on the table, it's a 1 in 5 chance.
Okay.
And then but once you pick yours, and now there's only 4 on the table for the next person,
Oh,
could be
so
a
it's
little
not
more
each person
complicated.
puts all the phones.
right? Because now, first of all, there's only 4, and maybe theirs was already chosen, or maybe it wasn't chosen. It turns out, by
Okay.
the way, mathematically to be 1 in 5 no matter what, which is kind of cool, but it's not so obvious. But the beautiful thing here is that we're not going to do a theoretical. We're going to do an empirical. We're actually going to perform multiple runs of the scenario. So how about we just put A, B, C, D, and E on 5 cards. So each card gets a letter, A, B, C, D, or E. And then we shuffle them and draw them in the order of person A, person B, person C, person D, person E. So the first card drawn, that was what A picked. The second card drawn, that was what B picked. The third card drawn, that was what C picked. The fourth D and the fifth E. And then what do we look for? What are we going to record for that run that we just did? What are we actually going to write down as our conclusion?
Who picked up their phone?
Yes, which card matched the person picked? Or specifically how,
Responds with, yeah.
right, or specifically how many, right? How many of the 5 cards were chosen at the right time? Does that make sense?
Yes.
Okay, and that's one run. That is one run. And then we do it again. And then we do it again. And then we do it again. And then we do it again, and so on. Okay, so let's say we do this 100 times. Let's say we do it 100 times. So we're going to get various, do they even ask that here? Okay, so they say conduct 6 runs. Okay, and it says record the number of students who got their iPhone for each of your 6 runs. So let's assume, let's just pick numbers. These numbers might be realistic, there might be not, but of the 6 times we did the run, let's pick a number for how many times nobody got their own iPhone. 1 person got their own iPhone, 2 people did, 3 people did, 4 people did, or 5 people did. Now, before we fill in any of these, one of them must be 0. Which one of these must be 0?
The first
First
one?
one. Would it be
Think about it. Think about it.
Wouldn't it be 5?
5?
Is it?
Okay.
Wait, are you saying it's impossible for all 5 to get their iPhone? Is it physically? No, I'm not saying it's mathematically impossible, but is it physically impossible that all 5 got their own iPhone?
No.
No.
Wouldn't it be, but it's unlikely.
Right?
It's impossible for 4 of them to get their own iPhone. Because if 4 of them got their own iPhone, what did the 5th person get?
Their iPhone.
They had to, right? It is impossible for 4 of them to get their own iPhone. Are all the other ones possible? Can nobody have gotten their own iPhone? Is that a possibility? Sure, of course.
That's a possibility.
Of course. Could 1 person have gotten their own? How about 2 or 3 or 5? Are those all possible?
Yes.
Sure. But the only one that's impossible is 4. Because if 4 get their own iPhone, then it has to be 5. So the question is, of your 6 runs, let's pick what we think are realistic numbers for all of these scenarios. How many times did all 5 get their correct iPhone if we ran the simulation 6 times? What would be a realistic outcome for this box? How many of those 6 times did everyone get their phone?
0.
Yeah, I would assume it would be very unrealistic. very unrealistic for each of the 5 to get their phone. In fact, you know what the probability is for each of the 5 to get their phone? 1 in 120. So it's less than a 1 in 100 chance that all 5 got their own phone. How about none of them got their own phone? Of the 6 times, how often do you think that occurred? What will be a realistic value for that?
4 out of 6.
Okay, 4 out of 6. 4 times out of the 6 runs, nobody got their phone. What's realistic for 1 person got their phone? And remember, only 2 runs left because 4 of them, nobody got their own phone.
That beaten 2?
Possibly, maybe twice it happens, and therefore this never happened and this never happened. So this is a realistic scenario. Of the 6 runs, 4 times nobody got their own phone, and twice 1 person got their own phone. Now, if these are our values, then what are the estimated probabilities of how likely it is that nobody got their own phone, or 1 person, 2 people, 3 people, 4 people, or 5 people? What values would I put here for their estimated probabilities? And remember, we can only use our data, not theory. What does our data tell us about the likelihood that everyone gets their own phone?
Zero.
0%. It never happens. So our best guess is 0%. How about 4 people get their own phone? Well, we know that can happen. So this is an exact. How about 3 people get their own phone? What does our data tell us about that?
0% as well.
0%. How about 2 people get their own phone?
0%.
0%. Never happened. How about 1 person got their own phone?
20%?
30%?
Not 20 or 30.
33%, right? Because it's
Close.
1/3.
It's about a third, right? 33.3 bar, if I want to be exact, percent, 2 out of 6. And what would the 4 people getting their own phone?
4 out of 6.
4 out of 6, which is 66.6 bar percent. So our estimated probabilities would give us this, which of course add to 100%. So according to this, it would never happen that 2, 3, 4, or 5 got their own phone. Now, of course, if I ran more runs, 100 runs, 1,000 runs, 1,000,000 runs, do I think those would all remain as zeros? Or do I think, as rare as they are, it should happen now and again, 2 people or 3 people or 5 people getting their own phone?
Yeah.
Yes, right? So the more runs you do, the more accurate your probabilities are going to be, which is basically what we learned in the first chapter of the law of large numbers, right? The more runs you do, the more your likelihoods will settle in under true values. Does this make sense so far? And how we don't actually need iPhones to actually run this experiment. We can just do it with index cards and get the same results as if we actually had iPhones. I mean, of course, cool people have Androids. We all know this, but for those uncool people who have iPhones, you know, we don't need them. Agreed? Yes,
Yes.
no, maybe so.
Yes.
So what's your conclusion here? What is your estimate of the probability that no student will get his or her own iPhone? What is our conclusion here? What's our estimate?
66%.
66? Yeah, 66.6 bar percent, about 67% and so on, based upon our run. Okay, now, up until now, we did cards, we did dice, we did spinners, we did coins. Now we're going to use random digits. Okay, and random digits are a very, very, very popular method of simulation. In order to use random digits, of course, you have to have what's called an RNG, a random number generator. You have to have something that can actually generate random digits. I once proposed a question to a student of mine. I said, is it possible that a person could randomly spout off numbers and have them be really random? Just like start recording numbers, 1, 3, 7, 9, 2, 6, 4, 8, 3, and so on. Just start recording digits. And the question is, can a person actually be random when they do that? So I had the person record their voice on tape for 5 minutes straight, just randomly sprouting digits for 5 minutes. And then afterwards, taking those hundreds and hundreds and hundreds of digits that they said, possibly even thousands, and making a table as to how often they said every digit. If it purely was random, how many times, or at least what percentage of the time, would you expect every digit to have been mentioned? If it really was random.
Roughly equal amounts of time.
Roughly equal amounts, which is 10%. 10 digits, 10%. Okay, but people tend to have favorite numbers. People tend not to think of some digits. So people cannot be random. It's not humanly possible. But computers can get pretty close. Computers can get pretty close to random. So anytime you have a random number generator, it is usually generated by a computer. So last year, 60% of CSUN's bachelor's degrees went to women. I select 20 graduates at random, and I want to count the number of women. Essentially, I am checking whether or not this is true. Okay, or I believe it's true, and for whatever reason, I want to see how many women I get in a grouping of 20. So what I do is I generate random digits. Now, how many digits do I have here in this random sequence? How many digits do I have?
30.
I have 30, but I don't need all 30. I just need 20. So in this case, even though my generator has this many digits, I'm going to throw these out. I don't need them for this particular problem. And I look at the first 20 digits. And now what I need to do is I need to create a scenario where there's a 60% chance of one outcome. So women, 60% chance, and non-women, I'll say non-women, 40% chance. How can I use digits, random digits? How can I create a scenario that has a 60% chance of one outcome and a 40% chance of the other outcome? I want to model this with digits. So how can I do that?
Could you do like 0 through 5 representing women and then 6 through 9 representing non-women? So you'd have 6 digits and then 4.
Love it. Since the digits are all equally likely, then any 6 digits versus the remaining 4 digits would be a 60% versus 40% scenario. So by picking specifically 0 to 5 as women and 6 to 9 as non-women, in the 20 students that I asked, how many of them were women in this particular example?
Well,
So I think I got 13. 1, 2, 3, 4, 5, 6,
Yeah,
7, 8, 9, 10, 11, 12, 13. 13 women, 7 men. That was one run. I got 13 women and 7 non-women. Is that roughly something that I would have expected if I actually asked 20 graduates rather than simulating the scenario? Would that be something in the vicinity of my expectations?
Yes?
Yes, roughly.
Yes, because if I ask 20 people and 60% of them went to women, what is 60% of 20?
13.
Not 13. That might be what I got here, but what is 60% of 20?
12.
12. Right? 10% is 2, so 60% is 12. So my expectations, and we will actually learn later in the course about what's called expected value, but my expectations are that I would get 12 women, so 13 women seems pretty close. This is similar to the problem that we had earlier. If I scroll up to the kindergarten scenario, we saw that I certainly expected, in this case, to have between 7 or 8 boys, but I saw that I had many situations where I had different amounts, but I was certainly nearer to my expectations more often than I was away from my expectations. So 13 is fairly close to my expected value of 12. Does that make sense? Yes, no, maybe so, hopefully so. So let's do another one. It says a common core standard for 7th grade is design and use a simulation to generate frequencies for compound events. So, for example, use random digits as a simulation tool to approximate the answer to the following question. If 40% of donors have type A blood, what is the probability that it will take at least 4 donors to find one with type A blood? I want you to think about that. How would I design a simulation to answer this question? Okay, we got someone to type something. She said, I apologize, I'm late. That does not answer the question, but I do appreciate the apology. It's very, very nice. I'm going to stop sharing for a second so I can record your attendance. So meanwhile, everyone else, think about this question while I go ahead and do this.
I was a little late too.
Who's I that's speaking?
Sitlali Garcia.
Gotcha, thank you. Okay. And just for the record, Michael and Emily, did you ever show up? No, Michael or Emily. Okay, so back to the file. Okay, so let me share screen again. And okay. Anyone have a thought for how to answer this one? Anyone?
So using the random digits,
Okay.
for this, wouldn't it be like finding a specific number in between, like, so like, let's say like, since it's 40%, you would go from 0 to 4. Type A could be like,
Well, first, I want to stop you there for a second. It's not 0 to 4. It's 0 to what would be 40%?
To 3, because we count 0 as a digit.
0 is a digit, right? So 0 to 3 is 4 digits. 0, 1, 2, 3, right? 4 digits, correct?
yes, sorry.
I forgive you. So non-A, the other type, non-A, would then be 4 through 9. Okay, so what we've done is we've matched. We've matched every outcome with one of our true outcomes of the actual scenario. But now tell me how to run the simulation. So I did interrupt you. So if you want to keep going, I think I interrupted you midstream there. But the question is, how do I run the simulation now?
That's where, like, I'm not sure. So would it be like finding one specific digit in between, like the 0, 1, 2, 3?
So
And
are you?
that?
So you're saying generate a random sequence of digits, but only generate one?
No, I'm saying generate a random sequence. See that, I don't know.
It's okay. I prefer wrong answers, or even, answers that kind of veer off in the middle, to just sitting there in silence. So I love just attempts, even if they're wrong, because maybe you'll say something that'll jar or jog someone else's thought process and they'll be able to finish it. So I love that. I love the collaboration. Okay. So does anyone else would like to venture a guess as to how I can simulate this scenario? No one?
So in that case, would it be that since they're saying that it will take at least 4 donors,
Yeah.
would you skip like every 4?
So not exactly. So here's how I would do it. I would generate 4 digits at a time. And I would check these 4 digits to see if I have a type A amongst those 4. If I have a type A, actually, let me rephrase it. Sorry. So let me actually do not 4 at a time, but rather 3 at a time. Not 4, 3. And then I would check, is this type A? Is this type A? Or is this type A? If any one of them are, then it took less than 4 donors to find one with type A blood, correct? And I would say that's a situation where I got it. So if any one of them are, but if I have all 3 of them not type A, I can stop and say in this run, it definitely took at least 4 to find one with type A, correct? Because if the first 3 did not have it, then maybe the 4th did, or the 5th, or the 6th, or the 7th. I don't even care. But I know that if the first 3 didn't have it, it should take at least 4, correct? Does that make sense? So,
Yeah, it makes sense.
so if any of these are a yes, then the answer is I got it. And if all 3 of them are no, the answer is I don't got it. And then what I'll do is I'll do this 20 times for a total of 60 digits. 20 runs, 60 digits. Because each run is 3 digits. Right? So 20 runs is 60 digits. And I'll count how many times of those 20 runs did I get the type A blood amongst the first 3 that I asked, and how many times did I not? And then the number of times that I didn't divided by 20 will be my approximate probability for taking at least 4 donors to get type A blood. Does that simulation make sense?
I'm confused why you're picking to generate, like instead of 4 digits at a time, you're doing 3.
Because if I don't get a type A blood amongst the first 3, then I know for a fact it's going to take 4 or more. right? It'll take at least 4 donors, correct? So I only need 3 to come to a conclusion. Does that make sense?
So it's because it says the keyword at least 4.
At least 4 means 4 or more is all part of what I'm looking for. So if I miss it in the first 3, I don't care whether it actually takes 4 or 5 or 6 or 7 or 8. That doesn't make a difference to me. It took at least 4.
So then
Yeah.
if you do have like the 4 digits and none of them are, then their conclusion is correct.
Well, I don't need 4. If I have 3 digits and none of them are, their conclusion is correct. If this is type O and then type B and then type O again, I can stop because I know it'll take at least 4 to get type A. Right? I can stop after 3 and conclude it'll take at least 4. I don't actually need to do 4 runs or 4 digits. 3 digits will allow me to conclude what I'm looking to conclude.
Yeah. So there's the guarantee that the 4th will be type A.
It's not a guarantee, but it is guaranteed that at least 4
Yeah.
are necessary before I get type A.
Yeah. Okay.
That's when you will answer at least 4. So we would just leave it at that. So it will take at least 4 donors to find one with type A blood.
Right. Well, the question is, what is the probability that it takes at least 4? So I have to count how many times it took at least 4. Let's say it took it 16 times to get at least 4 out of my 20 runs. So the probability would be 16 over 20 or 80%.
So it's like Katerina, sorry, I'm not sure if I'm saying your name right, but it's like she said it's because of the keyword that it says at least.
Well, that's
So sorry,
Yeah.
it's a little bit confusing. Yeah, I'm sorry.
no, nothing to apologize for. We're all learning here.
Mhm.
So what you need to do is create a scenario where you can ascertain whether this occurred or not. Whether it takes at least 4 or does not take at least 4.
Well,
And I know that if I do not get one in the first 3, then it certainly takes at least 4.
okay.
So I only need to check 3 before I can come to a conclusion about whether or not it takes at least 4 or not. And then I count how many times it took at least 4 versus how many runs I made, divide, and that will be the answer to my question.
And then why did you do 20? I'm sorry.
Oh, I just picked a random number that I thought was large enough to get a nice probability.
Oh, okay.
I mean, if I only did it one time, then my answer would be either 0% or 100%.
Oh, okay. Perfect.
Right? So I need to do a large enough number where I can get at least somewhere in the vicinity of being close.
Okay. I
So,
think I-
so let's
Thank
do
you.
it. No problem. So let's do it here. I don't see 60 digits, but let's see how many we can do here. Okay. So the first 3 digits. Did I get a type A blood?
Yes.
Yes, right?
Yes, because remember 0 to
You
3.
said in the first 3, yeah.
Right, 0 to 3 was in the type A blood, correct?
Yes.
How about the next 3 digits?
No.
Yes.
Yes, there's a
Wait,
0.
I'm sorry. Yes, sorry. Yes.
Okay, how about the next 3 digits?
First 3, yes.
Yes. How about the next 3 digits?
Yes.
How about the next 3 digits?
Yes.
Okay, so 5 times. How about the next 3 digits?
Yes.
Yes, 6 times in a row. How about the next 3 digits?
Yes.
7 times in a row. How about the next 3 digits?
Yes.
Yes, 8 times in a row. How about the next 3 digits?
No.
No. How about the next 3?
Yes.
So 9 out of 10 times. Next 3.
Yes.
10 out of 11 times. Next 3.
No.
So that's what, 10 out of 12. And next 3.
Yes.
Okay, so 11 out of 13 times, I got it in fewer than 4. So the probability of being at least 4, the probability of at least 4, and my handwriting sucks, I know, is approximately 2 over 13. Because of my 13 runs, it happened twice.
Perfect.
Does that make sense? I can even go 14 because I didn't even finish the last
Professor?
one, but I can really see a 1 there.
Professor, I have a question.
Yeah, go ahead.
I'm confused on the part on how do you know it's a yes or a no?
Because we decided 0 to 3 was type A and 4 to 9 was not type A. Otherwise, because I needed a scenario of a 40% chance of getting type A and a 60% chance of not getting type A. So I picked randomly 0 to 3 to be type A and 4 through 9 to be not type A. So in any triple, if a 0 to 3 appears, then I know I got a type A.
Okay, Professor, can you move your screen up? Because I don't know, I'm not
Is it
able.
cut off?
Or, yeah, it's cut off.
Well,
Like,
I can
I
move it
wasn't-
off.
Oh, I see.
Tell me what the lowest
Uh,
thing you see is.
Well, we see the Y, well, I see all the Ys, the X's, but just the line of it. And I
Yeah.
thought you were writing something under it, but I could not tell until.
So do you not see the digits there?
No, we can see.
Mm,
I think it's just a line that he
Oh,
actually.
yeah, I would just grouping them in by threes. I just made I don't know why you can't see it though. I see it on my screen. Oh, actually, you know what? No, you should be able to see it there. I can see it on my iPad. So you should be able to see the lines. You don't see them?
Yeah, I don't see it, but I don't know. I have like my toolbar down
Oh.
on the bottom.
Maybe that's it. All I did was I
Yeah.
put lines like these underneath them just to group them in by threes.
Okay,
So I just grouped them by threes like that. Does that make sense? Now, we did it with 13 or 14 runs, but they wanted us to do it with 50 runs, which is, of course, an even better approximation, right? The more runs that we do, the better the approximation is going to get. So let's find a table of random digits. It says there's one at the end of the lesson. So let's just jump ahead just to see what a real random number generator looks like, or a table. Maybe it's after the homework. Is that it? No, it's just a small one.
I think it's after or in the homework, the very last page.
Last page of the homework. Oh, hello. There we go. Lovely. So what I would do here is I would do it. That's a yes. That's a yes. That's a yes, and so on. And I would just go through 50 runs. That's a no. That's a yes. That's a yes. That's a no, and so on. Does that make sense? Yes?
Yeah.
And then
Yep.
and then out of the 50, you count how many of them is a yes, and so on.
What?
Say again?
Oh, I'm sorry.
Does that make sense?
Yep.
Okay, and of course, the more you do, the more accurate it is, which is why we like doing multiple runs. Of course, why do we not like doing multiple runs? Because it takes longer to do them. So there's always the battle between how much time we take and you know, what our goal is for what we want to learn. Now, in this situation, I did it one way and they did it a different way, which is totally fine. What they did is they just said, go until you get a type A blood. So what they said is my first run ends here because I got a type A blood in the first three. I got it right off the bat. Next run, ooh, got it right away. Next run, ooh, got it right away. Next run, took 3 times before I got it. Got it right away, got it right away, got it right away, got it right away, got it right away. Took 2 times to get it, got it right away, took 2 times to get it, took 2 times to get it, took 2 times to get it, got it right away, took 3 times to get it, took 4 times to get it, took 3 times to get it, got it right away, took 1, 2, 3, 4, 5, 6 times to get it, got it right away, and so on. So they did it differently. But that's the beautiful thing, is that there's more than one way of running a simulation. As long as the probabilities are correct, it doesn't matter how you model it. Different people can model it different ways and get different results depending on how many runs they make. Does everyone see what I did here in terms of what my model represents?
Yes.
Yeah, first one, I checked them. Hey, type A blood, start again. Type A blood, start again. Type A blood, start again. No, oh, no, oh, got one, start again. So how many runs do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 runs. And again, 2 out of 21 was the likelihood of not, this is not the answer for their question. Their question was, how many donors did it take to get one with type A blood? The answer is 1. We got one right off the bat. The very first donor had type A blood. Because what was the very first donor? This one right here. Does that make sense? Am I saying words that kind of hopefully come across?
Yes, Professor, I have sorry, I have a question
Yes.
about the 40% that's in the question.
Yeah.
Is that relevant?
Well, yeah, because the 40% is what we use to decide that 0 to 3 would go for type A and 4 to 9 is not type A.
Oh, okay.
We needed a situation that created a 40% versus 60% simulation.
Gotcha. Okay.
Right?
Thank you. Yeah.
So if we had said instead that it was a 50% chance, then our numbers would be different.
Okay.
Does that make sense?
Yes, it does. Thank you.
Okay. And of course, the conclusion would be, based upon my data, there's a, what I had before, I had like 2 in 19 or something like that. There's a 2 over 19 chance of needing more than 4 people to get type A blood. Now here's a follow-up question, which is very similar, but it's a little more challenging. Suppose 46% of donors have type O blood. What will be the probability that it takes at least 4 donors to find one with type O blood? 46%. See, 40%, that's great with 10 digits because I can assign 4 of the digits to this outcome and 6 of the digits to that outcome, and I have a 40% versus 60% simulation. But how do I do digits with 46%? How can I create a scenario with 46% or 11%? How do those numbers work?
Would it be the use of decimals or fractions, or is that too complicated?
Well, remember, we're doing random digits, correct? Random digits, we saw what random digits look like, right? So here's a, where's the next one? Well, okay. Well, let's just go to the table here, which I know is coming up. Suppose here's my table of random digits. How can I use this table to create a simulation with a 46% chance of occurring? Anyone see it?
Yeah, we see it.
I know. I'm saying I want to see the answer. Anyone see the answer to the question? How do I create a scenario that I can divide numbers into 2 categories, one of which is a 46% chance of occurring, and the other one is a 54% chance of occurring?
You take 46 of the blocks of the numbers and do something with that?
What do you mean 46 blocks? Like 46 digits long?
No, those squares of the numbers.
Oh, like a full block here?
Yeah.
I like the thought, but no, that's not correct. I think the easiest way is to assign the 2-digit pair 0 to 0 to the 2-digit pair 45 as being type A, and 46 to what digit 2-digit pair would be non-A?
99.
99. In other words, use 2 digits at a time. If you want a 46% chance, then we need to create 46 outcomes out of 100. So the first value is 29. What is 29 referring to here? Type A or not A?
Type A.
Type A. How about 56?
Not type A.
Not type A. How about 61?
Not type A.
63?
Not
23?
A.
So if the first run was just stopping at 29 because they found someone to type A, that's a run of 1. The next one would take 4 people to get type A. And how long would the next one take to get type A?
2 people.
Well, 92 is no, 98 is no, 82 is no, 29 is yes. This one also took 4 people to get type A.
Well, there's 23 in the other one, right?
Well, that's this run here
Oh, okay.
was from here to here. The 4th person was 23. Now we're starting over again.
Oh, okay.
4th person was 29. How about the next one? How many people did it take to get type A in the next one?
2.
2. 63 and 4. How about the next one?
1.
1. 44. Next one.
1.
1. 29. Next one.
2.
2. 20. Next one.
1.
1, got it right off the bat. Next one. 1, got it right off the bat. Next one. 2, and so on. 56, 75, 84, 71, 27. This one took 5. And so on and so forth. So you can use 2 digits at a time to create a scenario. Does that make sense? As long as the percentages match perfectly, it is a valid simulation. So if I need a 46% chance of occurring, if I take numbers in 2-digit blocks, 46 pairs go with A, the other 54 pairs go with not A. Does that make sense? I hope so.
Yes.
I hope
Yeah.
so. So if I go back here to the scenario here, what if I'm doing 11%? What if I have a situation of 11% of donors have type B blood? How can I use 2 digits at a time to create an 11% scenario?
Zero, 0 to 1, 0.
0, 0 to 1, 0. And how many, this is not at least 4 situation. I would just check one at a time. And how many times would I do my run for this particular example?
25.
25 times, right? 25 times. It says, what's the likelihood that none of them will have type blood? So what I can do is I can look at 25 people. That's 50 digits, right? Because every person is 2 digits. I can look at 50 digits at a time and see how often those numbers appear. If the answer is no, not once, then hey, none will have type B blood. I have a success. If it occurs at least once, nope, that's a failure. At least one will have type B blood. Does this make sense? These different approaches of simulations? Is it a little clearer than it was before? Is it still like, what is this guy talking about? Somewhere between scale of 1 to 10. Scale of 1 to 10. 1 means I can't even understand what language he's speaking, to 10 being, this is the easiest thing I've ever seen in my entire life. Give me some chat here. What are we at? 7. Okay. 6. Good. 5. Okay. 6.
7.
Okay. 4, 5. Okay. So somewhere somewhere in the middle to the better end. Okay, I'll take those, especially for a first time through. And then what happens? You review it. You do homework. Your homework solidifies your understanding. You get a little better. You're not always going to understand everything immediately after a teacher explains something, especially if it's challenging, which is why you go over it. But we're going to do more. We're not done. So let's do more simulation stuff. Hopefully by the time we're done, the numbers will go up a little bit. So it says McDonald's placed one of 8 teeny beanies, which I really hope is not a real thing, in each Happy Meal. Are those real things? Teeny beanies? Anyone? Those are real? Really? Seriously? Wow. Okay. You want to estimate the probability that a child gets the same teeny beanie in the first 2 Happy Meals that he buys. Describe how to use random digits to conduct one run of a simulation, and not all digits need to be used. How would I use random digits to conduct one run of a simulation here? First thing you have to do is look at the probabilities, or you have to assign numbers to different outcomes. How many different outcomes are there?
8.
8 outcomes, but how many digits are there if we want to use one at a time?
One?
Only one digit? There's only one digit? How many digits are there if we use one at a time?
8?
No.
Isn't it 9 counting 0?
Actually, it should be 10 counting 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 digits, correct?
Yes.
Right? So there's 10 digits that we can use, but we only want a scenario with 8 equally likely outcomes. How can I use random digits to create a scenario of 8 equally likely outcomes when I have 10 equally likely outcomes in my random number generator? How can I fix that?
Can you skip 0 and 9? So like 0 would be like they don't get one of the little toys, and then since there's only 8, you can't get another one.
Oh, hold on a second. Don't you automatically get one every time?
Yeah, so you'd ignore the 0.
But what does it mean, ignore the 0? What is that physically representing if I get a 0? That's my question. What does a 0 physically represent? It can't represent not getting one because you always get one, right?
Yeah.
So what would 0 physically represent? So the answer is 0 and 1 represent a do-over. They don't count. It's as if nothing happens. And 2 through 9 will represent my 8 different outcomes. So these are the 8 outcomes. In other words, if I get a 2, that means I got teeny beanie number 1, whatever that is, the blue one. And if I got a 5, I got, right, this is 2, let's say, and 3, and 4, 5, 6, 7, 8, and 9. Those are my 8 rewards. So as my simulation, if I'm looking at my random numbers and I see a 0 or 1, I just skip it. I mean, it doesn't count. Do-over. Nothing happens. I need a scenario of 8 equally likely outcomes. So because of random numbers, I can't generate that by using all of them. What does it say? Not all digits need to be used. So 0 to 1, I just straight up ignore. Does that make sense? So what is the probability that a child gets the same teeny beanie in the first 2 Happy Meals that he buys? when I look at my first two numbers, what am I looking for in these two numbers?
A number from 2 to 9.
Well, but there's two numbers here, right? I'm looking at, that's the first one that he buys, and that's the second one that he buys. So I need a digit to represent his first buying, and I need a digit to represent his second buying. What digits?
Let's do 6 and 4.
Okay, let's say you got 6 and 4. That means I got the little purple dolphin.
Yeah.
Okay. And then I got the pinkish.
The turtle.
That's a turtle.
Yeah, it's a turtle.
I don't think that's a turtle.
Yeah, it's a turtle. It's owl.
I'm sorry.
A turtle.
How does he fit his head in the shell? The head's like bigger than the shell itself.
Yeah, I know, but it's a turtle.
Okay, we'll have to disagree on this one. But anyways, so if the first two digits were 6 and 4, what does that outcome represent? Did he get the same teeny beanie in the first two Happy Meals?
No.
No. Now let's say he did another situation where he got 7 followed by a 0.
Do over.
Do over. I would look at the next digit, and let's say that was a 7.
Yes.
Then this would be a situation where I did get the same thing twice. And then I keep going. Every time I do this run, I can do it 25 times, 100 times, whatever it is. And I count how many yeses there were divided by how many runs. And that will be the likelihood that he got 2 of the same teeny beanies. Oh, okay. I see the owl here. That's definitely an owl.
Yeah.
Yes, that's an elephant. I got that.
Yes.
That's an alien of some kind.
The monkey.
That is not a, I don't, what are you seeing right now?
Ask the class. They'll tell you.
It
It's
is
a
a monkey. I see a
monkey.
monkey too.
The little ears.
Yeah. And
The
then
little ears. That's how you can tell it's a monkey by the, you know,
There's tail sticking out on the left, very.
yeah.
okay, this is an octopus, right?
Correct.
Okay, what's this one here?
A cat.
Unicorn.
Unicorn.
Sorry, yeah, unicorn.
A unicorn cat? Got it. A unicat. Got it. A unicat. We should make a new animal. And what in the world is this? I don't even want to know. What is this one?
Bear.
Either a bear.
Bear. What are you guys saying?
That's a leopard.
I thought it was a
Or a
leopard.
leopard.
Yeah, I thought it was a cheetah.
Leopard for sure.
For sure. For sure. Okay, that's it. She says for sure, so we know it is. What makes it a leopard?
The spots.
What spots?
Do you know the spots?
Really yellow spots with the blue around it.
Yeah.
Yeah. Next time we come to class, I'm gonna find like the teeny weeny identifier animal thing.
Great, scared me like that. Okay, perfect. Okay, so 50 runs and they come to the conclusion, yada, yada, yada. Fine. Okay.
Professor,
Yes.
can I ask one more question about that last one?
Yeah, it better not be about the teeny beanies though. Go ahead.
I still don't really understand why we used 0 through 9 instead of 1 through 8.
Oh, we could have used 1 through 8.
Oh, okay.
Well, the thing is this, one second. There are 10 digits, correct? We can't get around the fact that there are 10 digits in the number system. That's how we know we have 10 fingers, we have 10 toes. This is how we've created a number system. So when I do my random number generator, it can be anything from 0 to 9.
Oh, I see now.
But 0 to 9 are not 8 equally likely outcomes. They're 10 equally likely outcomes. So if I pick 2 of the numbers to be do-overs, they don't count. The remaining 8, whatever they are, whether it's 2 through 9 or 1 through, I don't care which ones you pick, but you got to create a scenario of 8 equally likely outcomes. Does that make sense?
Yes, thank you.
Okay. Okay, so a class completed 500 runs of the iPhone activity using a computer simulation. For each run, they recorded yes if exactly one person got their own iPhone, and otherwise they recorded no. And as they did this, they made the graph on the next page. So this is their graph of 500 runs for the probability that one person got their iPhone. First, let's look at this in the context of last chapter. Does this illustrate the law of large numbers?
Yes.
Yes.
Yeah, right. We have major fluctuation followed by stabilization. And it stabilizes approximately at what number, if you had to give a guess? What does it seem to stabilize at?
30.
Like
Yeah.
35%.
It looks about 35%. Maybe it's 33%, 1 and 3. Maybe it's 35%, 7 and 10. I don't know. I'd have to do the math. I thought it would stabilize differently in my head, but okay. So this is where it stabilizes. I can actually probably do the math, but it will be, it wouldn't take just a couple seconds. I'd actually have to do it. But it says, what were the results of the first 6 runs? So the first one is down here. That's a no. Right? That's a no. That means then it went up to the next one, which is here. If it goes up, what does that mean?
Yes.
Yes. It then goes up again. What does that mean?
Yes.
Yes. It then went up again. What does that mean?
Yes.
Up again. What does that mean?
Yes.
And then it dropped. So what does that mean?
No.
No and no, and then it's all over the place. Show how the proportion of yes was computed after the 6th run. Well, after the 6th run, we have a no, we have a yes, a second yes, a third yes, a 4th yes, followed by a no. So there was 4 yeses in the first 6. What is 4 over 6 equal to? Correct. I love it. 66%. You guys are very vocal and fantastic. So that's where it makes sense. It is 3:15. I do not want to keep you. We did not finish chapter 2. I think we're pretty close to the end, but we didn't quite finish it. So we will finish it on Thursday, and the homework will be due the following Thursday. And remember, homework 1 is due this Thursday, and expect a quiz on homework 1 to be given over the weekends on the material from chapter 1. So I'm going to stop sharing now. Are there any further questions on anything we did so far today? And if the answer to that is no, then I shall see you all on Thursday.
Thank you.
Stop recording.
Bye,
Thank
Professor.
you.
Bye, guys.